All right. Differential equations. This lecture will be about how to use our understanding of physics in our analysis of the brain, as well as how biology uses physical principles to perform the incredible feats that it's capable of. The class will consist of a general introduction to differential equations, how to deal with them, a quick jump to multiple variables, and then the Hodgkin-Huxley example that we're somewhat familiar with, and then different properties of dynamical systems at the end. A differential equation is a mathematical equation that relates some function with its derivatives. Solutions to differential equations can be either a single function or a class of functions, and we've seen this kind of thing before when we did the indefinite integrals and we had that plus c because the constant was not defined. Integration can actually solve very simple differential equations, for example this one right here. Alright, so this is a pretty simple differential equation. It just means that the slope of the function is defined at its y value. That means for when it's higher, that means it's going to be increasing faster. This can actually be solved using integration, and we're going to play a little bit fast and loose with the notation here, but it's alright because it kind of works. So what we do is we get 1 over y dy equals, and then we just integrate each side. And then we just ignore one of these c's because if I just subtracted it from the other side, we just have a different constant on the other side. And then we raise each side by e, so e to the ln of y to cancel out the ln here, and then we get this means that this differential equation has a class of solutions, and they're all of the form y equals c times e to the x. And so no matter what this c is going to be, it will satisfy this differential equation. All right, let's try a little bit more complex differential equation. And let's just go over a little bit of notation again. This is the same as saying and so these all mean the same thing, same notation as from the last lecture. This is an example where you can actually just use straight integration to solve it. And in the end, a lot of the ways that you actually end up solving differential equations is knowing a little pattern and a little bit of guess and check. So I'm going to just show an example of this, which is a solution, and I'm going to show that it's actually a solution. So if I take the derivative of this, and so when we actually add these up, we just get 2 times negative 3 is negative 6. And so we see that this solution actually works. You might have noticed when you were looking at this that another solution actually works, and that's just simply which just gives us which also solves the equation. So there's different ways to get different solutions, and if you're actually solving them out, then you have a pretty simple differential equation. Um, you'll notice that a lot of these solutions have the form or use the exponential, and that's because it doesn't decay as much or disappear when you take the derivative, and it still has the same form. Later, when we're talking about the time series stuff, we'll find a way to write sine and cosine as in the form of an exponential using complex numbers, and those are another example of those are also used in differential equations, and you guys know that the derivative of sine is actually cosine of x, and that can be written in terms of differential equations as well. All right, and so briefly, the way that we actually go about solving differential equations is by re-expressing it as a first order system. So and we just do this by doing a little bit of change of variables. So let's call y equals x1 and y prime equals x2. And so if we then differentiate this, we can get y prime equals x1 equals x2, and y double prime equals x2 prime, and it also equals to, going back to our original equation, 3y minus 2y prime. So 3y minus 2y prime, which is also equal to 3x minus 2x. And so now we just have a system of equations, differential of a system of first order differential equations that we actually end up using linear algebra to solve. And so that looks like it's and we can just use some rules to solve this. But in general, most differential equations can't actually be solved explicitly, and so you're going to end up numerically solving them. Even though we can't actually solve all the differential equations, one thing we can do to visualize a differential equation and try and get an intuition on what it's doing is called a slope field. And so what a slope field is over here on the right, at each point in this grid, it points a line, or it displays a line with the slope defined as whatever the slope needs to be in order to solve this differential equation. And so this is just the differential equation of the exponential family differential equation that we looked at previously. And you can see that all the solutions are going right along parallel to each of the lines in the slope field, and that different initial conditions will actually give you, or different constraints in general will give you different solutions to the differential equation. All right, so now we're going to talk about how to numerically solve these, or at least go over something called Eulers Method, which is a general idea of how to solve them, even though more modern methods are a bit more sophisticated. So let's say we're solving our same equation here, and we know it's an exponential, but we wanted to, let's just say we wanted to solve this numerically by hand. And so what you would do is you would say, and now we have an initial condition which defines a single path. So we say y of 0 equals 1. So this is our point here. Let's go blue. And so we would have our initial point, and then we would calculate what the slope it should be at that point. And so I'm going to create a table here, x, y, and the slope. And I'm going to end up taking steps through the space of delta x equals 1. So we start at 0. Our y value is 1 because of the initial condition. And then dy dx is just going to be equal to 1. So that means our slope is going to be 1. And if we're then taking to the next, if we're trying to figure out where the next point is going to be and we're using a delta x of 1, then we just use this slope of 1. If we're moving over 1, we're moving up 1. So our next point is going to be at 1, 2. And so we're just doing a linear approximation here. And so second y value is going to be equal to 2. And so now we calculate what the next slope should be, and since we just plug it into our equation and we get 2, and so our slope is 2. So for our next delta x, 3, if we want to move up 2 in the y direction, then we're going to be at 4. And so go up here, somewhere right here, and so this is our estimate of the next point. Now our slope is 4, and so our next x is going to be at 4, and the next y value is going to be 4, our original y value, plus the slope, the change for moving over 1x with the slope of 4, which is going to be 8. And so we get up to here, and this is our next estimate. And if you know what the exponential curve is of just e to the x, it goes something like this. And so we are slightly off here, but I'm doing this by hand with pretty large step sizes. And if we do this in a computer, we can get very small step sizes and get pretty accurate estimates. And we can also do better estimates than just taking a single point and estimating the slope at that point. All right, now a little bit about multivariate differential equations, and that just means that there's going to be multiple different variables that are varying across time or space, and from the last lecture, we already know what a multivariable derivative is, and if we're actually just going to be numerically solving, like we're going to be for pretty much every case we're interested in, there's not very much difference in actually solving a multivariate differential equations. And I guess the proper term for a multivariate differential equation is it's a partial differential equation from the partial derivative that we learned about last class. This is a classic example of a partial differential equation, and this is the visualization of heat transfer in a pump casing. So it's just the heat equations that Newton came up with back in, I don't know, 1700 something. And it's just applied to a very specific case where of this specific heat casing for a pump, and heat is generated internally, and there's it's being cooled at the boundary, so it heat transfers, and you can solve for the steady state heat distribution, temperature distribution. All right, I just wanted to mention here that all of physics is differential equations, or at least all of Newtonian physics is differential equations. Forces affect the acceleration, force equals ma, and acceleration is the second derivative of motion. Current is the change in charge over time, or the movement of charge over time. Electric fields, magnetic fields, gravitational fields are all slope fields that explain the force, i.e. second derivative. It also describes how many ions flow across a membrane when a channel opens, or how likely a channel is to be open is also a differential equation. And what I mean by that is Hodgkin-Huxley came up with this model based on physical measurements that they took of the giant squid axon, and they came up with the dynamical system, or the differential equations that describe the membrane of the giant squid axon, and was able to generate action potentials. And so we're going to play around with this a little bit in lab with a MATLAB demo. But I'm assuming most of you guys have heard of Hodgkin-Huxley by now. All right, I accidentally used the phrase dynamical system a minute ago, and I guess I ought to define it. A dynamical system is simply a system in which a function describes the time dependence of the state of the system. It's nothing magical about it. If your differential equation has ddt in it, then they describe a dynamical system. There are theoretically dynamical systems that aren't differential equations if you have discrete states or something like a Markov model, but mostly people refer to differential equation-based dynamical systems. Next class, we'll talk about ways to look at dynamical systems where you don't know the function or the underlying equations, but for now, let's introduce some of the concepts behind dynamical systems, or the concepts used to analyze them. Phase space is the space of all possible states of a system and has the number of dimensions equal to the number of time-varying variables in your equations. The system's evolving state over time traces a path through the space and is called a phase space trajectory through the high-dimensional space. And so here's an example of a spiking neuron model and its phase space. In figure 8, voltage is plotted on the x-axis against a gating variable, and you can see the comparison to time broken out into B and C. You can see that one spike is a path through the space, or is a trajectory through this space. And in fact, the system's movement through the space doesn't have to be at the same time. So you can see that the red and black represents the longest actual drawn distance in the phase space, but actually represents only a small fraction of the actual time of the system. Figure D here is representing the idea of a limit cycle. So let's take a closer look. A limit cycle is a path or trajectory through the phase space that at least one other trajectory spirals into it, or either as time approaches infinity or negative infinity. What this means is, or from negative infinity, it means that this is an unstable limit cycle, and that no matter how close you get to the limit cycle, it will eventually leave and spiral off. Figure D here is actually demonstrating a stable limit cycle, because even if you perturb the system or start from a point that's off the limit cycle, the path will actually eventually take it back to the limit cycle, and it will converge there as time goes to infinity. And so it's convergent from both sides, because if you start from over here, it will also go towards the limit cycle. Also note that the existence and the exact shape of the limit cycle are highly dependent on the parameters you use in your equations. And this is another example from a different model or a different set of parameters. And it's also possible to have multiple limit cycles of a system. When this happens, you have what is called bifurcation. So here's an example using our spiking model of bifurcation. And so our bifurcation variable is going to be the input current that we put into the cell. And we can see that at a certain point, maybe maybe around 10 nanoamps, there's a large change in the behavior of the cell, even though the actual parameter that we're varying changes only like an infinitesimally small amount. So this is the exact opposite of stability. A small change in the parameter can have very different outputs. And so the the limit cycle, or the trajectory of these, is plotted here on the left, and you can see that even though they start at nearly identical places, the trajectories are very different. If you remember back to, or I guess you might not have been to the lecture, but this is actually how ears can detect vibrations that are smaller than the size of an atom, and it's because they set up their position in this phase space so that they're directly on a bifurcation point. And so if a vibration occurs that slightly pushes it over the bifurcation point, then they can detect it using the nonlinearity of the bifurcation. All right, here are the resources, and by resources I mean these are the Wikipedia pages that I have open that I had open when I was making this lecture. There are lots of Khan Academy videos and other videos if you want to learn how to solve differential equations explicitly or analytically, but hopefully the demonstration in class through the problem set will actually be really helpful for you guys to understand how all these